Now, in the previous session, we have come to know about the regression equation uh, between the variable x and variable y. There were two regression equations. One is called y on x, and another regression equation is called x on y. Now, let me write the regression equation once again, because one important point I need to discuss before I go into the details of how to find out these regression equations. Now, the thing is that when we write y on x, this particular word means y is dependent on x. That means you are considering y to be your response variable and x to be your input variable. Whenever we are writing x on x, this means x is dependent on y. That means here capital X is your response variable and capital Y is your input variable. The regression equations were given by the following form. As you can recall, one regression equation was y minus y bar r into sigma y by sigma x into x minus x bar. Another regression equation was like this: x minus x bar r into sigma x by sigma y into y minus y bar. Now, do not think that this regression equation, as you can see, while writing the regression equation y on x, we have kept y terms on the left hand side and x terms on the right hand side. We have kept sigma y on the top of sigma x. And you have also observed that while writing x on y, regression equation x on y, we have kept x terms on the left hand side, y terms on the right hand side, and has kept the standard deviation of x on the top of standard deviation of y. Do not think that one equation can be derived from the other. Now, if someone thinks that, okay, y minus y bar is there, x minus x bar is there, and we want to find the regression equation of x on y, so we don't have to recall the second equation. We can derive the second equation from the previous one. We need to keep x minus x bar on the left hand side. We have to take y minus y bar on the right hand side, and then sigma x will automatically be on the top of sigma y. But what he can miss in this process is that 1 by this r will come as a reciprocal. Okay, now this equation that I have written and that equation, they are not same. Remember, and if you write it like this is actually not regression equation of x on y. So if you write like this, actually you are not writing the regression equation of x on y. You are actually writing regression equation of y on x in a different form, actually. Okay, so you have to be very serious about it, careful about it, that this should not be done. So there are two lines of regression. If you are treating the variable y to be the response variable and x to be the input variable, the first one is your item, and this, if you do the opposite, the reverse, then the second one is your objective. The second regression equation is what you want. Now, where comes the part E? That E I was talking about. It is very simple. Now you have got these values x and y. The values of x and y were 1, 2, 3, 5, and values of y were 4, 7, 8, and 12. You have got your relation, estimated relation, as follows: 1.914x plus 2.485. This is your estimated relation. Now, if you put these values of x over here, okay, definitely these values that you will obtain will be different from capital Y. Suppose this value after putting x equal to 1 is y1, this value is y2, this value is y3. I'm not calculating it. You can do it by yourself. Then E, which is called the error term, is actually the difference between the estimated value and the observed value, the actual value. So their difference, the difference between y1 minus 4, y2 minus 7, y3 minus 8, and y4 minus 12 will give you this difference. If you calculate it, will give you the error term. So that is what we know, we termed as random error. Now, suppose what happens is that why it is said that this error has mean 0. It means we have got 4 values. Carefully listen to me. We have got 4 values for the variables capital X and capital Y, 4 set of values. Now, we have calculated correlation coefficient between them. Regression equation has been found, and some error terms have been found. Okay, some error terms have been found. 4 error terms have been found. This is our analysis for the first day. Suppose this analysis is done by one of our students from CSE section A on day 1, June 2021. After 1 week, another student of CSE section A takes the same physical system, collects 4 values from the physical system, does the analysis, finds correlation coefficient, regression line, and the errors. And then on the 3rd week, another student repeats the same process. And in the 4th week, another student repeats the same process, and it goes on. After 6 months, that means after 24 weeks, but we'll have 24 error terms in front of us. Now, if the students are not manipulating the results, if they're honest enough to choose the result from the physical system, and we have in our hand 24 different error terms. Okay, so this error term, as you can say, it is E1. Then another student is finding it E2, then E3, and in this manner, you are calculating E24. After your analysis of 6 months, then you can also calculate the mean of these error terms, which will be considered as E1 bar. This will be E2 bar. This will be E3 bar. And that will be in this manner. If we go on, this will be E24 bar. Okay. Now, if I consider the mean of these items, E1 bar, E2 bar, E24 bar, if I consider the mean of these items, okay, that means all these mean values, all these means of errors will be added and will be divided by 24, which means E1 bar plus E2 bar plus ... plus E24 bar by 24. If I do so, then it will be approximately be equal to 0, or it may become exactly equal to 0. Okay, so that is why it is called that the random error has mean 0. This is the meaning of that. Now, one more thing that I want to discuss in this particular case, that since we have 2 regression lines, look at these terms that I'm going to highlight right now. This term R into sigma y by sigma x, which comes from the regression equation y on x, and this term, which is called R into sigma x by sigma y. Okay, these terms are actually called regression equation of y on x. These terms are actually called regression equation. Sorry, regression, not regression equation, sorry, slip of tongue. Regression coefficient y on x. And it is denoted by byx, which is given by the formula R into sigma y by sigma x. Second coefficient is called the regression coefficient of x on y, and that will be bxy, which is r into sigma x by sigma y. And if you observe, you will see that if I multiply this regression coefficients together, if I multiply them together, then what we are going to get is the following. We are going to get this, which is r square. So it is a very important result, which says that correlation coefficient squared, correlation coefficient squared is equal to product of two regression coefficients. Product of two regression coefficients. Okay, this is very important result. You have to note it down. Now, if the values of the variables, are not known, are not given to you, but if I tell you that the equation which is there in front of you is a regression equation, and if I'm not telling lie, then you can directly find out the correlation coefficient from the equation itself. Okay, so for example, if I give you an equation of the following form, so if I say that, okay, one of my regression equation is this is my regression equation, and if I say that, okay, this is my regression equation y on x, and another regression equation that we have is x on y. Okay, if I say this, and if I'm not wrong, then immediately after this declaration, if I have to declare that, if I do not declare it, you cannot do the calculation. And I'm saying that it is regression x on y. So in this particular case, what will happen is that, okay, not 2. Its equation has been written in a wrong way. I have to correct it. Suppose I'm giving it in the following manner. Suppose I'm saying that this is the equation. Okay, then what will happen is that if I say so, you can immediately identify byx from here, which is 2, and bxy from there, which is half, and you will find out that if such equation is there, the correlation coefficient between them will be equal to 2 into half whole squared. No, not 2 into half, sorry, 2 into half, that is, this value is 2 and that value is half, which is equal to 1. And 1 can be written as 1 squared. So correlation coefficient between them, these two variables are x and y, will be equal to 1, and they will have, x and y will have perfect correlation, will have perfect correlation. Remember, this can only be done if you have the knowledge that the equation that you are dealing with is the regression equation. If the equation is not the regression equation, then you cannot proceed in the following manner. Every regression equation is a linear equation, but not all linear equations are regression equations. Regression equations are actually found in a special way that I have not yet discussed, but I will discuss it in due time. So there are some methodologies by which that can be done. But I think for your online examinations, first of all, you have to know about the properties of the regression coefficients well. So this is the first property that I'm actually I wanted to discuss with you. The second property that I'm going to write over here is as follows. The second property is as follows. Okay, let us write the property. If you can call this as property 1. Then property 2. Then property 2 is if one of the regression coefficients is greater than unity, then the other one must be less than unity. Okay, how to prove this result? Suppose byx is the regression coefficient which is greater than unity. To show that bxy is less than unity or less than or equal to 1. Now we know that r square is less than or equal to 1. R is the correlation coefficient between the two variables. And r square is given by the property 1 as byx into bxy. This should be less than or equal to 1. Okay. Now this implies bxy is less than or equal to 1 by byx. But as we have already assumed that byx is greater than 1, this automatically implies that byx is less than 1, isn't it? 1 by byx is less than 1. So here we have obtained bxy as less than or equal to 1 by byx, and which is less than 1. So this implies bxy less than 1. So the result is proved. Now you see that probably you have not missed. When teachers do something wrong, students actually don't miss it. Okay, they like to find out the errors from teachers' end. So if you have not missed, probably you have seen that initially I gave you the regression equations to be x equal to 2y. I told you that this is one regression equation and that is another regression equation. Immediately you can say that immediately you can tell me that no sir, you are telling wrong. This cannot be, because if you are saying that y equal to 2x plus 3 and x equal to 2y are the two regression equations from the same set of data, they can be the regression equation from different sets of data. But if they are regression equation from the same sets of data, sir, you are wrong, because we have already come to know from the property 2 that if one regression equation is greater than unity, as we can see, the other regression equation must be less than unity, but you have kept it greater than unity, and according to you, your correlation coefficient will come out more than 1. So this property 2 is getting violated, sir, over here. So these two equations, regression equations, cannot be part of the same physical system. They can be part of two different individual physical systems, sir. That you can tell me. Okay, very important, just keep in mind. Now another property that I'm going to explain is that the modulus value of the arithmetic mean, I'm writing it as am. Okay, I'm writing arithmetic mean as am. The modulus value of the arithmetic mean of the regression coefficients is not less than the modulus value of the correlation coefficient R. The modulus value of the arithmetic mean of the regression coefficients cannot be less than, is not less than the modulus of the correlation coefficient R. What is modulus value? Modulus value means absolute value. So we know that we have two regression coefficients byx and bxy as regression coefficients. Okay. And R is the correlation between the two variables. If we assume that the given result is true, that means half of the arithmetic mean of the two regression coefficients byx and bxy, the absolute value of that is not less than the absolute value of the correlation coefficient R. This will in turn imply, we can separate the modulus sign. We can write it as in the following manner: byx plus bxy is not less than R. If it is so, and half is the positive quantity, so we can remove the absolute sign. So we have byx plus bxy. This should be greater than or equal to R. This implies, now you substitute the formula for byx, which is R into sigma y by sigma x, plus bxy is R into sigma x by sigma y. This should be greater than or equal to R. This implies, inside the modulus, you take the LCM, which is sigma x sigma y, and that should be equal to R. Oh, here mod R was there, sorry. So absolute value of R will be considered. So if I do so, you will get R into sigma y squared plus R into sigma x squared, which should be greater than or equal to mod R. This will imply half into, take mod R outside, and inside we will get sigma y squared plus sigma x squared by sigma x into sigma y. That should be greater than or equal to mod R. Now on both sides we have mod R, so this mod R and that mod R will cancel each other. So this will imply mod of sigma y squared plus sigma x squared by sigma x into sigma y greater than or equal to 2. Now carefully observe that sigma x squared and sigma y squared, this is x squared and sigma y squared, they are variance, and variance is always positive. Sigma x squared is a variance, it's always a positive quantity. Sigma y squared is a variance, it is always a positive quantity. Sum of two positive quantities is always a positive quantity. Product of two positive quantities is always a positive quantity. And absolute value of the positive quantity is a positive quantity. So what you can do is that you can remove the absolute symbol from the left hand side and you can just write it as this. Now, if you subtract 2 sigma x sigma y from both sides, you will find a perfect square like that, which is always true, which is always true. Okay. So what we find is that we started with this assumption to be correct, and if we assume that this result needs to be correct, then we ultimately reach to this conclusion. This conclusion is not an absurd conclusion. That means our assumption regarding that the arithmetic mean of the two regression coefficient is not being less than the correlation coefficient, this is actually holding over here. This is actually true over here, isn't it? Now, this result, you do not just you have seen the proof of this result that I have done just for you, but only seeing the proof and doing it, uh, uh, practicing it in your copy or applying it somewhere will not help you. You have to keep these results in your mind. I'm not talking about the online examination only, because if you are fond of machine learning, this regression equation part, regression analysis will come again and again into the picture. Okay. Now I'm going to discuss another property. Let us call it as property 4. Now this property is regression equation, regression coefficients are independent of change of origin but not of scale. I shall quickly do this particular problem. Okay, we have two regression coefficients, byx and bxy, and we have the variables, and let x and y are the two input and response variables. Two input and response variables. Okay, now in this particular case, I'm going to change my x to a new variable u. And you already know that the formula for u's actually in this regard is x minus a by h. When I subtract the quantity a from x is called the change of origin. When I divide the quantity x by h, it is called the change of scale. So I'm going to do this operation on both these variables. I'm going to change in the similar fashion. I'm going to change y variable too with the introduction of the constants b and k over here. So the origin is being changed to b and scale is being changed to k. Now a and b, h and k, all these constants are taken to be positive constants because h and k are divisors, and divisors are always positive quantity. To be on to make the thing simplified, we have considered this thing as positive. Otherwise, it is not a hard and fast rule that this should always be positive. You can consider something which is negatively shifted linearly. So I am avoiding that scenario. Okay. If I do so, we see that the correlation, the covariance between UV, the covariance between UV is actually covariance between the term x minus a by h and y minus b by k. And in one of the earlier calculations, once I told you that this can easily be shown to be equal to hk covariance of UV, covariance of xy. You can repeat the calculation. If you want to do the calculation, this you can take the help of this formula of covariance in terms of expectation. In one of my earlier classes, I told you about that. So in place of capital X, you can substitute x minus a by h. In place of capital Y, you can substitute y minus b by k. Simplify and this will come out. Also, we know that sigma u squared will be actually equal to h squared into sigma x squared, and sigma v squared will be actually equal to k squared into sigma y squared. So these are the results that you can get from calculations. I'm not going into the details because it has been told to you several times. Now, what about byx? let us try to find it out, because we are interested about the regression coefficients. Let us choose byx without any loss of generality. Byx is given by the formula r into sigma y by sigma x. What is the formula for covariance of x? What is the formula for correlation coefficient of x and y? The formula of correlation of between x and y is covariance xy by sigma x into sigma y. So I'm writing it over here, and this is multiplied by sigma y by sigma x. Now sigma y and sigma y will cancel each other. So in terms of covariance of xy, you have got this formula. So byx is given by covariance xy by sigma x squared. Okay. Now with in terms of new variables, you have already found in terms of new variables. Okay, just I have done a mistake over here. I just interchanged the things. Okay, just a minute. This will be equal to x comma y. And this will be equal to, this term will not be there. This term will not be there. Let me write it in a proper manner. Okay. I just interchanged the input and response variables. Okay, because when I wanted to substitute the thing, I found this particular error. Since I'm not doing the calculation, you can start from calculating covariance of UV. Then that would be actually equal to 1 by hk into covariance of xy. And this thing will be sigma x squared, and that will be sigma u squared. This will be sigma y squared, and that will be equal to sigma v squared. Just rectify these parts. Now you can substitute in place of covariance xy, you can put hk into covariance uv. In place of sigma x squared, you can put h squared sigma u squared. And you find that we get the constant to be k by h, and that will be equal to covariance of uv by sigma u squared. Now carefully observe that if byx is given by this formula, that covariance of xy by sigma x squared is byx, then covariance of uv by sigma u squared will definitely be equal to b vu. So what we have found, we found that the regression coefficient between x and y, the regression coefficient between x and y, and regression coefficient between v and u, they are actually connected, but the scales, the quantification of scales, small k and small h, are actually present inside the formula. But there are no, in the relation this, there are no terms like small a and small b. So regression coefficient, if you change the variable, if you change the origin, shift the origin of the variables, it will not affect the regression coefficients. If you give it a linear shift to the positive side, or if you give the linear shift to the negative side, it will not affect the regression coefficient. But if you change the scale of measurement, then it is going to affect the regression coefficient in great amount, in the ratio k by h. Okay, so this is actually very important. And there is another property, property 6. It is actually asking us to find the angle between, the form of the angle between two lines of regression. Okay, so let me quickly find it out. One regression equation you know is given by y minus y bar r into sigma y by sigma x into x minus x bar. Another regression equation is given to be x minus x bar r into sigma x by sigma y into y minus y bar. I want to compare these two equations with one another. Now, to do this, I want to express this regression equation as the following: y minus y bar is equal to 1 by r into sigma y by sigma x, so that in both these equations y minus y bar remains on the left hand side. Okay, so this is another form of equation B. If I compare these two equations, comparing A and B, we find that slope of A, if we denote this by m1, is r into sigma y by sigma x, and slope of B, which is m2, this is 1 by r into sigma y by sigma x. Suppose theta be the angle between the two lines, then you know already that we have got this relation. The angle theta is the angle, not I'm considering here the acute angle between the two lines. Then tan theta will be equal to modulus of m1 minus m2 by 1 plus m1 m2. Now here in this particular expression, you can substitute the values of m1 and m2, and if you calculate and simplify the thing, you will find this expression. We do not have time now left for this particular session, so I'm going to directly write it. You just try to calculate this properly. If you find any difficulties in finding this expression, then you can ask me later on. Modulus sign will not be there, with the same logic by which we avoided modulus sign in our earlier calculations, because sigma x, sigma y, they are positive quantities. So we have this expression will come. Try to do this calculation. Okay, and if tan theta is like this, then theta will be tan inverse that. Okay, so theta will be equal to tan inverse 1 minus r square by mod r sigma x into sigma y by sigma x squared plus sigma y squared. Okay, now from this you can have several analyses. You see, if r equal to 0, if the correlation coefficient between the variable is 0, then tan inverse is 0. If tan inverse is 0, no, tan inverse is in that case is equal to, correlation is 0, is that means we get theta to be tan inverse infinity, and if theta is tan inverse infinity, then that means theta is pi by 2. So if the movement of one variable is like that, another variable will perpendicular to that. The movement of another variable will be perpendicular to that. So they are independent of one another. And if correlation between them is 1, then we get theta to be tan inverse 0. And in that case, for perfect correlation, the movement of the two variable will be on the same direction, either increasing or decreasing. So this much for today. I am going to end my